One of the things that we've been talking about in class is what does it mean for events to be independent? We've said what it generally means is that the outcome of one does not have any effect on the outcome of any other event. Well, there's more to it than just that, and there are two rules for independence that we can use to check to see if events are independent. That is, if you wanted to know if events A and B are independent of one another, then if you calculate the probability that A occurs, that will be the same as the probability that A given B occurs. It doesn't matter that B happened, A's probability should remain the same. That's precisely what it means to be independent. On the other hand, we can say also that the probability that B occurs will be equal to the probability of B given A occurs. So again, if we know that A happened, it does not affect the probability that B will happen. So if those two probabilities are not the same, then we do not say that they are independent, but rather not independent, or we use the term dependent. So say, for instance, we're tossing a fair coin, and we toss it 10 times, and all 10 of those times we get a head. Well, don't give your coin any more credit than is deserved. A coin does not have a brain. It does not remember that its previous 10 outcomes were all heads. So every time that that coin is flipped, the probability that a head comes up is always going to be the same. It's going to be 1/2. So it doesn't matter that there were 10 heads in a row. The probability of getting an 11th head will remain the same. It will be 1/2. Okay, so the outcomes of the flip of a coin are independent of one another. Therefore, the probability that the 11th flip will be a head is the same as the probability that the 10th flip was a head, which is the same as the probability that the 9th flip was a head, and so on. They are independent tosses. Okay, well, let's say we're going to do a combination here, and we're going to flip a coin, and then we're also going to roll a die. And we're going to combine the outcome of the flip of our coin with the outcome of the roll of our die. Well, there are 2 outcomes possible when you flip a coin, head or tail, and there are 6 outcomes possible when you roll a die, 1, 2, 3, 4, 5, or 6. So according to our multiplication rule, there are 2 times 6 total outcomes possible, or 12, when you combine the outcomes of your coin with the outcome of your roll. So if I say define event A as being a head and define event B as being a 6 on the roll of a die, well, we've talked multiple times in class that the probability of rolling a 6, because 6 is one of 6 outcomes when you roll a die, then the probability is 1/6 that you would roll a 6. If I say find the probability of B given A, well, that means that event A is that we got a head. It doesn't matter that we got a head. We still have the same probability of rolling a 6 on our die. So head or tail, regardless, the probability of rolling a 6 is equal to 1/6. So it doesn't matter what happened previously. The probability of rolling a 6 is 1/6. Because those probabilities are equal to one another, then we can say that those events are independent of one another. The probability of B is equal to the probability of B given A. The outcome of that flip of the coin did not have any effect on the outcome of the roll of our die. Well, we know, therefore, then, that when events are independent, we can find the probability that A and B both happen. Another rule is that you can take the probability of A and you can multiply it by the probability of B. Well, that works with multiple events. So if you want to find the probability that A occurs and B occurs and C occurs, and you know the events are independent, then you can merely multiply the probability of A by the probability of B by the probability of C. And you can find the probability that all three things happen. We can do the same thing with their complements. If we wanted to know the probability that A does not happen, and that B does not happen, and that C does not happen, then we can find, if they're independent again, the probability that all three of them don't happen by multiplying their individual probabilities together. Again, this only works when events are independent of one another. So let's say we're going to roll 3 fair dice, and each one of them has 1 through 6 possibilities. So you've got 6 possibilities on your first roll, you've got 6 possibilities on your second roll, and you've got 6 possibilities on your third roll. That means that the number of combinations of outcomes on roll 1 with roll 2 with roll 3 will be equal to 6 times 6 times 6, or 216. Well, there's only one of those 216 outcomes that will have a 1 on the first die, and a 1 on the second die, and a 1 on the third die. Therefore, the probability that you'll get 3 1s on the roll of those 3 dice is 1 out of the total number of outcomes, 216. So if I then asked you to find the probability of not rolling a 1 on any of those dice, that would mean we roll a 2, 3, 4, 5, or 6 on die 1, a 2, 3, 4, 5, or 6 on die 2, and a 2, 3, 4, 5, or 6 on die 3. There are 5 of the 6 outcomes that are not 1s. So the probability of not getting a 1 on any of those dice would be 5, 6 times 5, 6 times 5, 6. Again, we can multiply those probabilities because the outcomes of the roll of a die are independent of one another. And so we get a probability of 5 times 5 times 5 over 6 times 6 times 6, which is 125 out of 216. Now, Mr. Youngsaver addressed this in his video that we watched last week in class. If you wanted to know the probability then that you'll roll a 1 on at least one of the 3 dice, the complement of that would be not to roll, or would be to not roll a 1 on any of the 3 dice. Well, the probability of not rolling a 1 on any of the 3 dice was 5, 6. So the probability of rolling a 1 on all 3 dice was 5, 6 times 5, 6 times 5, 6. So the complement of that would be 1 minus the probability that we previously computed in part B. So it'd be 1 minus 125 over 216, which is 91 over 216.